Hi everyone, this is Professor Saida Falafini, and in this video I'm going to talk about some of the introductory concepts related to simulation. What is a simulation? Why do we do the simulation, and how it's helping us with decision making, and at the end the different type of simulations. So the first question is that what is simulation? At this point I want you guys to please pause your videos and think for a couple of minutes about what is the simulation, what is your understanding of this word, and what does it bring to your mind. Okay, simulation basically is a set of tools and techniques that we use to mimic the behavior of different systems. Most of the time it's done by a computer, but it can also be done maybe for simple systems with a paper and a pencil as well. So when we talk about simulation, when we talk about the simulation as a tool for mimicking the behavior of different systems, the terms that you're using are like systems, models, and behaviors. Okay, so before we get more into the definition of simulation and why we use simulation, let's look at some of these basic definitions. Okay, so what is a system? A system is a set of interrelated components that are working together to achieve some common objectives. Okay, so for example, if we think about an airport, it's a system. What are the components? Airplanes, different type of airlines, airport itself, passengers. These are all different components of this system that are working together such that this complex system achieves its objectives. For example, if you consider a call center, that's a system too. The agents that answer the calls, the customers that call, the telephones that are there, the building, the managers, all of these are different components of this system, and they're working together to achieve their common objective. The next question is that what do we mean when we talk about the state of a system? The state of a system is basically the situation or the condition by which we know or we recognize a system with respect to the value associated with some of its attributes. Okay, so let's see what it means. If you consider a manufacturing company, for example, what would be some of the attributes or characteristics of that system that we would like to know or monitor? For example, we like to know the profit of that company in each month. We would like to know how many customers they have had, what is their timeliness of response to the customers, and several other factors. Okay, so these are all metrics that maybe the management of the company has so that they can monitor the behavior of the system. So the collection of these factors, the collection of these metrics is at any point of time is what we call as the state of the system. The value of these metrics and the value of these characteristics form what we call as the state of the system. So at any point of time, we have specific values for these metrics, and we can use them to specify the state of the system. Now, if we monitor the state of the system over time, what we observe is what we call as the behavior of the system, how a system has behaved over time. For example, if we monitor some of the characteristics such as profit of a company, number of customers, the revenue, and so forth over time, what we are basically doing is that we are looking at the behavior of this system over time. If these factors are increasing over time, that means the company is doing good, the state of this company is good. But if these factors are decreasing over time, that means something is wrong in this system. So we have to stop the system and figure out what is going on, why our profit or revenue is going down, why our number of customers is going down. Okay, so basically in a system, we are always interested to know what are some of the characteristics that we want to monitor over time. Those characteristics form what we call the state of the system, and monitoring those characteristics over time is what we call as the behavior of the system. Okay. So the next question that I have for you is that why do we do the simulation? Why do we develop simulated models? So we do simulation because we can use the simulated system, the simulated model, as a virtual environment in which we can try and implement different policies and different solutions and different ideas and see how they perform in those simulated environments. And as a result, we can compare those ideas or those solutions and finally recommend the one that is performing better in the simulated environment. And that policy is going to be implemented in the real world. If, for example, in a manufacturing setting, we may not observe a high production rate, okay? We are not able to meet customer demands because our production rate is low, and we want to see what is going on. So we may want to do some analysis on the system, and we may see that the number of employees is not enough, or the number of machines that we have is not enough. So the question is that, okay, how many more employees we have to hire, how many more machines we have to buy. And so we can develop a simulated model of the production process, and in this virtual environment, in this simulated environment, we can implement different policies. We can change the number of employees, we can increase them or decrease them, we can change the number of machines, we can increase them or decrease them, and see how each one of these changes affect the production rate, and if that's exactly what we want or not. So if we were going to implement these policies or these solutions in the real world to try them, if we were going to just buy machines or hire or fire personnel in the real world and see if that's going to work, if that leads to a increase in the production rate, that would be a very costly and very timely process to go to finally see what is the best solution that we have to stick to. In a simulated environment with no cost and with a very reasonable short time, we can implement different policies and perform the simulation model and see how they perform in the system. And these bullets that you are observing here pretty much are a summary of what I just mentioned in terms of why we are running simulation model in a system. And also one other reason is that in systems there are different sources of variability. For example, if you are modeling a manufacturing system, the orders that come to the system may arrive at different points of time. The time that we need to spend to finish each one of the orders may be different from each other, and we don't know exactly how long the next order would take. So there are a lot of sources of variability and randomness in the systems, and we want to be able to predict behavior of the systems under those random situations. So if we want to do that, again, simulation environments are great for us to be able to do those analysis, to be able to model those systems and then see how the behavior or how the performance of the system changes over time. The simulation helps us to really understand or get a better sense of all these details that affects performance of the system, and to see how we have to change each one of them such that our system performs the most as the most effective and most efficient system that can possibly perform. So simulation has been used pretty much in any application area. It has been heavily used in manufacturing industry. As I told you, if we have a production line, we can definitely simulate arrival of the orders, arrival of the parts, and how they get processed in this production line, and how many we can produce, what is our production rate, what is our fulfillment time, and what should be our inventory level, and so forth. We can definitely do that. In service industry, it has also heavily been used. For example, in a bank or a call center, one of the main questions that we have is that how many agents we have to hire such that our customers don't need to wait in a long line in a bank or in a call center to be answered. But at the same time, we don't want to hire too many agents, because in that scenario, our customers may not wait as much, and that's good, but then we may have a lot of agents who are idle most of the times, and that's a lot of salary that we are paying, but we are not getting anything out of it. So And main questions for the bank manager or call center managers is that what is the right number of agents that I have to hire such that there is a balance between the salary I have to pay, which is efficiency of the system, and the responsiveness to my customer, which is the effectiveness of the system. So as I told you, simulation has been heavily used in manufacturing process, in bank or call centers. It has been used heavily in airport industry to design the airport, to see how many, for example, security check stations we need and how many agents we have to hire. In the restaurants, the same way, how many tables we want, how many waiter or waitress we want, and go on to supermarkets. For example, how many checkout lines we need at a supermarket such that our customers don't wait too long, but at the same time we don't have too many checkout lines that are just idle and empty most of the times. So as I mentioned, simulation has been heavily used in many areas in both and manufacturing industries. So there's no limit in terms of where you can use the simulation for the analysis of a system. The other concept that I want to talk about is different type of simulations. So there are different type of simulations out there to model and to mimic different type of systems. We can definitely categorize simulation systems based on their consideration of time. We can have dynamic systems or static systems. In dynamic systems, characteristic of interest in systems change over time. For example, if we are modeling a manufacturing system, the production rate over time would change, the time that it takes to meet customers' demand would change over time. So these characteristics of interest in this system change over time, and we just want to see how they change over time. Would they increase or decrease, or they may have some oscillation over time. But in static systems, the time doesn't have a role at all. The characteristics of interest don't change at all. Pretty much all the systems out there and a lot of simulation models that we develop are dynamic systems. They are simulations in which the time plays an important role, and we want to see how the behavior of the systems change over time. We can also categorize the simulation models in terms of being a continuous time simulation model or a discrete time simulation model. In continuous time simulation model, the characteristic of interest change continuously over time. For example, if we are interested to monitor the level of water in a reservoir or in a dam, we can that the level of water changes continuously over time. So in each specific day, depending on the level of precipitation we get, depending on the level of evaporation we get, the amount of water in the dam would change, and as a result the level of water would go up and down continuously over time. But there are also discrete time simulation models in which the characteristic of interest change at continuous points of time in the system. For example, if you want to know how many customers we are answering, for example, at every hour in a bank, what is the production rate at the production process. So these characteristics of interest will basically updated in the system every time a new part comes in or a new customer comes in, or every time a part goes out, is done and is leaving the system, or every time a new customer the customer gets the service and leaves the system. So that's basically what we mean by discrete time simulation model or discrete event simulation model. The characteristic of interest change at discrete points of time. We can also categorize simulation models in terms of being a deterministic system or a deterministic simulation or a stochastic simulation. In a stochastic simulation, a lot of the inputs in the system are stochastic or random. For example, the arrival time of the customers, or the arrival time of parts, or the arrival time of orders. These are not fixed points of time. These are random and they change every day. The time that it takes, for example, to provide service to each customer in a bank, these are not fixed. These are randoms, and it's different between every customer and the next one. So this is what we call with the stochastic simulation model. But deterministic simulation models are the ones in which the characteristic of interest are deterministic and they happen at fixed point of time. For example, if we are having a simulation model in which orders arrive every half an hour and they are processed exactly for 20 minutes, these systems are deterministic systems, or those simulations are deterministic simulations.